Good morning and welcome you. Hope you are fine. Uh, Today we are continuing our stress distribution chapter, that is for the advanced foundation engineering, and this is the last part of this chapter. So we start with this stress distribution lecture, that is part 3. In this part we are going to discuss with the now application of stress distribution first. As we have seen the some closed form solutions, some equation which we derived for a different nodes, that is the circular footing, rectangular footing, embankment load, etc. How that stress, that is sigma z vertical stress, is used to determine a consolidation settlement. So we'll complete that part, then followed by we'll see how the Newmarks chart is useful for finding the same sigma z, particularly for a irregular motion. So we'll see the first the settlement analysis, particularly the consolidation settlement. In a consolidation, if you remember, we have derived that the expression called as delta h upon h, and which is equal to delta E upon 1 plus E0. Delta H is the change in the thickness or final compression after the loading is over with respect to the depth, and at that time what is the void ratio. So we had various compressibility parameters. The first parameter from the consolidation test that was obtained is the relation between E and sigma, where we get a loading and unloading curve. The slope of the loading curve, we call it as a coefficient of compressibility, it is AV, and that we get delta sigma upon delta E upon delta sigma. Minus indicate only it is decreasing. Okay, we require a magnitude. So therefore we can write from here this delta E will calculate. So delta is equal to this AV into delta sigma, considering only the magnitude. If I substitute, so delta H is also called as a settlement, consolidation settlement. Symbol is S, or sometimes written as SC. So substituting this value in the equation 1, so we get AV upon 1 plus E0. Okay, then this delta sigma in H. And we know this AV upon delta sigma, this ratio is nothing but the MV, that is the coefficient of volume change. Okay, this already we discussed in our consolidation. So MV, delta sigma and H gives the first expression to find out the consolidation settlement. If you have just a coefficient of volume change, and that is because of that stress. If we know that difference of the stress, suppose it is applied 0.2 to 0.5, then here we are writing the 0.5 minus 0.2 difference of the stress with the original thickness of the strata. Now another parameter which is used in the consolidation test is the compression index CC. So if you see here, there is another graph that is the loading and unloading, same graph, but here the log is the XX and slope of this curve, you can see the black color, that is the laboratory curve, outside is the field curve. If you see that, so that gives us a CC, that is the compression index, delta E upon the difference of these two, but it is in a log, therefore sigma 2 upon sigma 1. Okay, so from this delta E is CC into this log of sigma 2 upon sigma 1. Okay, so using this, now if the strata is a normally consolidated, so normally consolidated means when the effective overburden pressure is equals to the sigma C, that is pre-consolidation pressure, sigma C or PC, whatever the symbol you use. Okay, so if you see in this curve, if I draw a field curve, we'll also discuss later, you'll find that this sigma 0 and sigma c, they are on the same line. So therefore this is called as the NC clay, and we can write the expression as sigma c upon 1 plus E0 into H. Now you can find out this delta E. If I find out delta E is equal to Cc into log of sigma 2 upon sigma 1, which is substituted here, and this delta E is again substituted back to the equation 1, then using Cc, you'll find that Cc upon 1 plus E0, this 1 plus E0 is as it is, into the height, and a log of sigma 0. This is sigma 2. Now how it is sigma 2? When sigma 1, let us say it is the effective overburden pressure sigma 0 dash, and now because of this, the stress distribution, what we say, that is the sigma z, which is called as delta sigma or delta sigma z. If that value is added to sigma 0, then it is sigma 2. So sigma 2 is sigma 0 dash plus delta sigma. So sigma 2 value is sigma 0 plus delta sigma divided by sigma 1 is sigma 0 dash. So this expression gives us a consolidation settlement. Okay. So in this case, to use this CC compression index by using a field curve, it will be a more accurate value. We get it to consider the effect of disturbance and all in the laboratory curve. So the simple construction is that here we as it is a log, so we cannot plot the 0 value, the reading at 0. So therefore here E0 value is plotted, and then a horizontal line indicate that there was no compression. Okay. And up to the sigma 0 and sigma c value. Then the end value is from the different observations, okay, by researcher. It is found that it is 0.42 E0. Okay, so this blue point is at 0.42 times of this E0. So I get the second point. It is nearly on the curve, either just above or just below, or sometimes exactly on the end point. And joining this straight line to this sigma 0 and sigma c line, the slope of this line, we get a CC field. Okay, so this slope of this straight line indicate the field curve. That slope, if I use here, so I get a expression called as the consolidation settlement for NC clay. So in NC clay, if I write a OCR value using this, I get the ratio is 1, because sigma c upon sigma 0 dash is a 1. Now if the strata or that clay deposit is over consolidated, okay, over consolidated means the OCR value is greater than 1. Okay, so if it is over consolidated, okay, so you can see the curve. This is the laboratory curve. So this test may be done in a cyclic also. You can see here the first cycle is completed, and at the end a unloading is done. It can be done in a number of cycles also. So this is a laboratory curve. Okay, so this is the unloading and this is the recompression. Again, you can find that this curve will not meet, it not go outside. It become a slightly curve, and then again join the same almost same straight line. If I draw this curve, okay, laboratory curve, then it follows the same. It will not go outside. Okay, so the slope of this unloading and recompression curve, okay, is called as the recompression index, that is the CR, this average through. Okay, so in a over consolidation clay, you know that sigma 0 value is on the left hand side, sigma c is on the right hand side, because sigma c is greater than sigma 0 dash. So this upon this, the ratio is greater than 1. So draw the horizontal line first. Okay, so because of this horizontal line, it cuts the point here. Then as it's a log curve, you cannot plot a 0, so you have a E0 value. So you mark that E0 value. Already we have seen in the last lecture using the table. I'll just go through that table quickly. Okay, just explain from the same figure. So sigma, this is the E0 value which is obtained from the consolidation test. Okay, and this is marked here, and again the straight line is drawn just like earlier up to sigma 0 dash. This indicates there was a no compression takes place in a field. Okay, then sigma CE line is marked. Then this the average slope here that gives us a recompression index CS CR. The same line is drawn parallel from sigma 0 dash, so it cuts the sigma C. Okay, and from the observations is again obtained at the bottom point is 42% of this E0, so 0.42 E0 horizontal line is marked, so where it cuts the curve. Okay, sometimes it is nearby, above or below, so that point is joined to the sigma C. Okay, so here we have two slopes, one is the CR, and now this slope indicate it is a CCF. Okay, so now we know this field curve. Now we have already calculated, suppose, a sigma z value which is called as delta sigma z here, that is from the stress distribution. Okay, so that is because of the external load. For example, there is a suppose a raft, so that is exerting a pressure of sigma z. Okay, so because of the sigma z there is a compression. Okay, so we know the sigma 0 dash value, that is the effective overburden pressure. For example, sample is taken out at 2 meter, so gamma or gamma dash into that 2 meter gives you the sigma 0 dash, and from stress distribution you got the value. If this total sigma 0 dash plus delta sigma, okay, suppose this is 20 and this is 10, so this become 30. If this is less than, suppose sigma c is 50, so still the OCR is greater than 1, but condition is that because this external load is causing a delta sigma, this difference, okay, it falls in between the two, therefore it causes, for example, this is a raft, okay, and this sigma 0 plus delta sigma is obtained from stress distribution, but this is causing a settlement, okay, and this compressing E0, okay, to a minus the delta E, so it compresses from one point to second point by delta E. Okay, so if the first point sigma 0 dash is sigma 1 and second point is sigma 2, so this sigma 2 is nothing but the sigma 0 dash plus delta sigma. Okay, so using again the same equation of delta E here, if you substitute in the using a CC equation, okay, so it is log of sigma 2 upon sigma 1, so the settlement equation you can write. Now you can see the slope settlement expression only between these 2 points delta E, where the slope is CR only. Okay, so here we use CR upon 1 plus E0 into H. Okay, using the same expression we are substituting in the first equation, that delta E, and again rewriting. Now how we write this sigma 2 and sigma 1, you can see here first stress is sigma 0 dash plus difference of these two. Here the total is sigma 0 dash plus delta sigma and sigma 0 dash. So if I take a difference of these two, sigma 0 dash plus delta sigma minus sigma 0 dash, so this sigma 0 dash get cancelled. So finally CR upon 1 plus E0 H log 10. Okay, this sigma 0 plus delta sigma upon sigma 0 dash. Okay, so it is the settlement between these 2 point 1 and 2 point only. Okay, so this is how we get first expression for a over consolidation claim. Okay, so Now we'll move to the second condition. Earlier we have seen that sigma 0 plus delta sigma is less than sigma c. Now suppose it is greater than sigma c. Okay, so again I drawn the same curve here, that is the laboratory curve, E versus sigma dash curve, that is this is on the log. And suppose here the consolidation is done with the one that is the cyclic test, and finally it is unloaded. The slope of this line gives you the CR here. Okay, so first you mark the sigma 0 dash line, then sigma c. So sigma c is greater than sigma 0 dash, OCR is greater than 1, so it is a OCK. And now this delta sigma, because of the external load, okay, for example like a raft or any circular footing or a raft, there the pressure is delta sigma, but the magnitude is such that delta sigma 0 dash plus delta sigma, okay, it crosses the sigma c line. So it means this load is beyond the sigma c. So because of that, how the settlement takes place from E0, so this point is again E0, A to B, the settlement is because of sigma 0 to sigma c, and the slope is CR. From B to C, okay, settlement is because of sigma 0 dash plus delta sigma to sigma c is because of the field curve. Okay, so field curve already I discussed. So this is CCF, this is CR. So here we get a two change in void ratio, from A to B delta sigma 1, from B to C delta E1, sorry, and delta E2. So total compression of the void ratio is delta E is equal to delta E1 plus delta E2. So therefore the settlement takes place from A to B is S1 and B to C is S2. Okay, so let us concentrate on the first delta E1, so to get the settlement S1. So here it is very clear that settlement is into two parts, S1 and S2, because of delta E1 and E2. So delta E1, so void ratio decreases, okay, due to sigma 1 is sigma 0 dash to sigma 2 is sigma cc. Okay, so over the stress range the slope is CR. So therefore the delta E equation, as we discussed earlier, okay, is minus cc log 2 upon 1. Substituting in the first equation delta H upon H, so we get a settlement S1, that is CR upon 1 plus E0 H log of. Now first point is sigma 0, and this is the difference between these two, sigma c minus sigma 0 dash. So sigma 0 dash plus difference between these two, sigma c minus sigma 0 dash. So sigma 0 dash cancel, okay, divided by with respect to the original sigma 0 dash, and therefore we get a expression CR 1 plus E0 H log of 10 sigma c upon sigma 0 dash. Directly also we can write, if you see the stress range is sigma c over sigma 0 dash, the sigma c or sigma 0 dash, because of the slope CR, because of the slope CR. Okay, so this is the first part of the settlement S1. Now second part, in a second part, that the from B to C, okay, the void ratio changes. So therefore at sigma 1 point is B, that is sigma c, and sigma 2 point is sigma 0 dash plus delta sigma. Okay, and here the slope is the CCF. So therefore the settlement because of this second void ratio, again substituting the equation, again we can write delta E equation, okay, and again we substitute in the first equation, that is delta H upon H, so you will find CC upon 1 plus E0, because the settlement takes place in this slope. Okay, and CC upon 1 plus E0 H. And now first load, it is at the sigma 1 is sigma c, okay, at difference of these two. Okay, see the delta sigma is always measured from sigma 0 dash. Okay, so sigma 0 dash plus delta sigma, okay, minus sigma c is written here, okay, with sigma c as a base. So therefore sigma c get cancel. Okay, and finally it is left sigma 0 dash plus delta sigma by 6. So it is okay, CCF upon 1 plus C0 H log of 10. Here it is sigma c is very important, because here the base value sigma 1 value is sigma c, not this one. Okay, so it can be directly written as sigma delta sigma 0 plus delta sigma divided by sigma c. So adding these two, we get a total settlement. So this is how a settlement for a consolidation settlement for a normally consolidated clay is obtained, as we discussed earlier, by the first simple expression, and then for OC clay it is obtained by in the first condition, this expression in terms of CR. And when the condition is such that delta sigma 0 plus sigma 0 plus delta sigma is greater than sigma c, the settlement is obtained in the two part. Okay, so this is how the total settlement in OC clay is also obtained. Okay, now we'll move to the one detailed problem. Okay, how this is used. So the next, okay, so let us solve one problem here. Let us say there's a tank, circular tank, say 6 meter diameter, and the total load upon area, that stress transfer at the base or foundation level is suppose 300 kilopascal, and the soil profile is like this. The top layer up to 2.5 is the sand, then 2.5 to 7.5 it is a medium stiff clay. Okay, and water table is at the top. See, the consolidation settlement it takes place, okay, when soil is fully saturated. Okay, this is a very important concept. Okay, so that's why the groundwater level is mostly at the top. Okay, then 2.5 to 7.5 is the medium stiff clay, and then 7.5 to 9.5. So this is for 2 meter. First is for a 5 meter, and this is for a 2 meter. Is a slightly stiff clay. This is a medium stiff clay, and this is a stiff clay. The sigma c value, consolidation test was carried out for the medium stiff clay and also for a stiff clay. Medium stiff clay gives a pre-consolidation pressure of 126. Saturated unit weight is given 80. This becomes a gamma dash because it is a submerged condition. Similarly, for second layer, saturated condition, gamma saturated given is 20 kN per meter cube. Okay, so gamma dash will be the 20 minus 9.81, and sigma cc from the sample which is taken and conducted a consolidation test gives the pre-consolidation value is suppose 93 kilopascal, and this sample which is taken medium stiff clay has a complete E versus sigma 0 dash versus E data can be analyzed separately, and it also separately. But for simplicity, the average value from say the test 1 and test 2 is given here. Okay, so apply stress, and because of that, what is the change in void ratio? These are given. Okay, when stress is 0, it increases 0.2, 0.5, 1, 2, 4. So this is the loading and then unloading, and you can see the final void ratio is 1.7 and initial void ratio is 2.312. So here we have to find out a consolidation settlement separately for a first layer medium stiff clay, and then we'll find out separately for a stiff clay. Okay, so this is the same problem. Okay. Now is to start with this. So first we find out a settlement of the first layer, that is the medium stiff clay. Okay, now first thing is find out, check whether it is a NC clay or OC clay. Okay, so first find out sigma 0 dash is okay at the center of the first layer. Okay, so it means in this figure, the elaborated figure, at the center, middle, this is the layer. At the middle we'll find out what is the sigma 0 dash, that is 17 into 2.5, and sigma dash, okay, this 18 minus 9.81 into this distance, that is 2.5, gives me the sigma 0 dash effective overburden pressure. Okay, so this value we get it at sigma 2.97. Now sigma C for this layer was at 126 pre-consolidation pressure given, so this is divided by this, so we get OCR is 2. Okay, so that indicates it is a over consolidated clay. Okay, so it means we have to find out the settlement by checking the which criteria, condition 1 or condition 2, for finding the consolidation settlement. Okay, so the first step what we'll do is to find out that delta sigma z by using our stress distribution concept. Okay, so yeah, you see the figure here, the settlement is always obtained at the center of the clay. So height of the clay is 2.5 minus 7.5, that is 5 meter. So settlement is obtained at the middle, which is 5 meter from the ground level. Okay, so to obtain this value, you can see the thickness is more, that is 5 meter. Okay, so what we do, we'll find out delta sigma value at the top of this layer, we'll find out at the middle, and we'll find out at the bottom delta sigma by varying the z value. Okay, using the expression for a circular footing, and then we'll take a average value. Okay, so you can see here how average value is taken. So average is taken as delta sigma z at the top layer, okay, the middle layer and bottom layer. So it is top layer 4 times of middle layer and the bottom layer. Summation divided by 1/6 gives me the average. Okay, so this is also one way to find out this the average. Now we know the expression for a circular load or circular stress, which exert the pressure Q. 1 upon 1 minus 1 upon 1 plus the radius of the circular here, that circular tank, divided by the depth. Okay. The first is at the top, so top that z value is 2.5. okay, Q value is given 300. So substituting that R is 6 meter is the tank diameter, so radius is 3 meter. So substituting Z as 2.5, 3 upon 2.5 square, square 3 by 2. So finally value we get it 221.289. You can see here as the stress goes down, depth increases, stress decreases. Now at the middle, where the depth is 5 meter, so here 3 by 5, okay, Z is changed from 2.5 to 3, okay, and then we get the value 110.847. So you can see the stress is decreased from top to middle, okay, and then at the bottom of the layer is 7.5, and how it is, so here 3 by 7.5, okay, square, and so finally we get 59.87. So to take the average, 1/6 of top layer, 4 times of middle value and the bottom value divided by 6. So you get the average value is 126.76. okay, so we have sigma 0 dash, now we have delta sigma dash. Okay, now we'll find out a settlement. Okay, as it is a OC clay deposit, okay, now the first thing is to check whether it is condition 1 or condition 2. So sigma 0 dash plus delta sigma average value, compare with the pre-consolidation pressure, which is 126, and the sigma 0 dash is 62.97, and just calculated sigma z is 120.76, so total is 183, which is much greater than 126. So therefore this is the condition, the second condition, okay, where sigma 0 dash plus delta sigma is greater than sigma c. So just I'll show you once again that this is the same condition, okay. Sigma 0 plus delta sigma is greater than sigma c. So settlement is taken from S1 and S2. So the first expression S1 and S2, okay. So the after finding this delta sigma 0 and then further calculating for the settlement, okay, you require the value of this CR in CCF. So therefore the it is necessary to construct the, you can see, the field curve. So first the lap curve is constructed, then E0 value is marked because 0 you can't plot here, so this value can't plot, so directly you can mark here, that is E0 value. Mark the sigma 0 dash value, that is 62.47. Mark the sigma c value, that is 126 kilopascal. So 0 to sigma 0 dash, that is a straight line that indicate no compression takes place. Then here only loading and unloading is done. Loading and unloading is done. So what we'll do, we'll take an average slope of this, okay, and draw the line parallel from sigma 0 dash, okay, which cuts the sigma c line. So I get this slope, and this slope is nothing but the recompression index, that is CR, okay. The second point you find out is the 42% of E0. Here in this case the value is much less, much below, 2.3, and this become close to 1. So this point come much below, okay. So selection of point, either it is dropping below or sometime we take it at extending this line where it cross the bottom, that point is considered as the bottom one, okay. So the fixing this point 0.42 is 0 and then joining this point to the intersection of this CR, so we get the CCF. So first slope we get it, okay, that is from E0 and this E1, suppose okay, difference divided by these two pressures, that is sigma c and sigma 0 dash, so we get a first slope. Similarly second slope is the CCF from sigma c, and the last value is 4, okay. Their corresponding difference in the void ratio gives us the slopes CCF, so which is equal to 0.289 and CR is equal to 0.04. So you'll always find that the CR value is much less than the CCF, okay. With some approximation, sometimes this may be half of the CCF field. So knowing these values, now we can substitute in the equation of the settlement. So first expression is CR upon 1 plus E0 log of sigma c upon sigma 0 dash. So substitute the values, okay. So CR value just now obtained from the construction field curve 0.0447, E0 from the table, first value that was a 2.312, and here the expression is sigma c upon sigma 0 dash 126 upon 62.97. So you get the value in meter, multiplying 1000 you get the value, a settlement in mm, 20.32 mm. So this is the first part, S1, okay. Now second part, write this expression. Now here we require CCF, which is 2.89, okay. In both the height of the clay, thickness of clay is 5 meter, okay, that is from 2.5 to 7.5. So substituting these values, okay, and again calculating, multiplied by 1000 you get 7.14. So you get total settlement 27.468. and this is how the consolidation settlement for this OC clay is obtained for the first layer, which was the medium stiff clay, which I showed earlier. So for first layer we got the value. Now we'll proceed for the second strut. Okay, so now settlement of the stiff clay. So this stiff clay exists from the depth 7.5 to 9.5, with the center or its middle is at the 8.5. Okay, CC is given 93, gamma saturated is given 20. This has to subtract from 9.81 because it is a submerged one. Okay, so again we'll use the same strata, same observation, because these are the average values for both the clay. Okay, again we'll plot this to find out again the CC value, compression index. Okay, so now first find out sigma 0 dash. Same procedure will repeat now. Okay, it is at the center 17 into 2.5. so I'll just show you again. 17 into 2.5, then this value is 18 minus 9.81, so this gives you the 8.19, okay, into 5. Okay, and then this gamma dash is minus 9.81, become 10.19 into half this, so that is 1 meter, 7.5 to 8 meter. So this become a 7 for 1 meter. So total gives us the 93.64. So first again find out the OCR, sigma c equals sigma 0 dash. So OCR sigma c value is given 93. This value is also close to 93. The value is very close to the 1. So therefore this strata we call it as a NC clay. So you can see here in a same deposit, the strata earlier was an OC clay and at a slightly below depth, okay, slightly deeper depth, it will become a NC clay. Okay, so again for the bottom layer 7.5, 8.5, 9.5, first we find out the vertical stress due to that the circular time at the top, middle and bottom. Okay, so again the average value we have written this, top 4 times of stress at middle and the stress at bottom. The stress at the top 7.5 is again writing this expression. So here the radius is 3 meter, r by z, z is 7.5, okay, power 2, total power 3 by 2 into q value is 300. So here the stress is 59.877 kilopascal. Then at the middle, substituting 8.5, z at 8.5, again calculating this, we get a stress at 48.439. and similarly at the bottom of that second layer, that is z is equal to 9.5. so substituting here z as 9.5, r by z, r is 3 meter, again by calculating this, okay, so this is 300 into so therefore the stress is 39.866. so taking the average, the top value 4 times of middle value and the bottommost value, addition of this with 1 by 6 gives the average value is delta sigma z. So we have a sigma 0 dash and we have a delta sigma z. So write down the expression for a NC clay, which is very simple. So before that, to find out the slope, because it is a NC clay, so again do the construction here. So first you draw the laboratory curve as we had drawn earlier. Okay, this is on the log. So this is drawn from point 2 to 4 meter. It's point 2 to point 2. Okay, 0 can't be plotted here because it is a log. So first from the table you know the E0 value, so mark the E0 value. Here we mark the sigma 0 dash. Okay, and now sigma 0 dash and sigma c both are the almost same, that is 93. So draw the vertical line, join this line. Okay, So this is horizontal, that means there is no compression takes place up to this point. Then find out this second point, 0.42E0, which come very close to 1, and you can see here I try to extend this line where it meets, and this point is join. Okay, the slope of this curve, this field curve, okay, this is the sample has experienced the first time is a new low. That's why you get a compression here. So find out the slope, which is 0.268 between these 2 points. Okay, write down the settlement expression. CCF upon 1 plus E0 H log 10 sigma 0 dash delta sigma average by sigma 0 dash. Very simple. Okay, concept is the same again. So substituting this value, CCF, which is obtained field value, is 0.268. Okay, and substituting this effective stress and the sigma and the delta sigma, which is the average value which we got it earlier, divided by sigma 0 dash. So settlement comes out to be 29.54 mm. Okay, so this is the expression which is this is the value which we got it. Okay, separately, the first value we got it separately, second value we got it separately. Okay, these two values are further corrected for a different corrections. Okay, these corrections are if the foundation is a rigid foundation. Okay, it means sometimes there is a raft, the thickness is very high, more than 1.5 meter or 2 meter or 2.5, sometimes 3 meter also for a high rise structure. Okay, so it's a very rigid foundation is there. Then we apply a correction of factor as a 0.8. Second thing is that the foundation is taken at a depth, certain depth of it. Okay, therefore the settlement at the depth and settlement at the surface is a difference. Okay, so there also we apply a correction factor, a depth factor. In this case, the tank is resting almost on the ground, so this correction is not applied. Second thing, the tank is almost a flexible base, so that rigid factor 0.8 is also not applicable. But third correction, three corrections. Third correction is for a three-dimensional consolidation, or it is also called as a pore pressure correction. Okay, though the consolidation we say that it is a one-dimensional. Okay, but actually there is a lateral compression takes place. So therefore, it also takes place in the radial direction. So to account for this three-dimension correction, okay, there is another graph is available. Okay, given by a germ, and from that graph you can find out that correction factor. Okay, I'll show you how to just calculate that correction factor. Okay, so this is the graph to find out the correction factor, okay, which is given by the skimter and the germ. Okay, so this is the factor, that multiplying factor is beta, and here a pore pressure coefficient. It means it is necessary to know the pore pressure coefficient for both the strata, medium steep claim and the steep claim. Okay, then only we can able to find out this factor. Suppose this value, suppose we are applying for a second layer as an example, and let A value is given as 0.7. So you can see here there are different graphs. This is the A. Okay, so the 0.7 will come here, and these graphs, okay, are available first for a circular footings, that is a solid line, and dotted line is for a strip footing. Okay, so this graph gives you another ratio by H by B. Okay, that is the thickness of clay over the width of footing. Here in our case it is the diameter. Okay, so in once you find out this, suppose
in our case, our thickness of clay is 2 meter and the diameter is is 6. So it is a 2 by 6, that value which we get it from this the curve. Okay, and so it is 1 by 3, around 0.33. Okay, so we have to select a graph for a 0.33. You can see this is for a first solid line for 4, then 1, then 0.5, then 0.25. Okay, so 0.33 means 0.25 and 0.5, and the 0.7, suppose a value I take it for pressure coefficient, then somewhere I get a value close to the 0.8. Okay, so this is how the correction B, that is the beta, is obtained. Multiply the settlement. So 3 correction factors which we use. First is for rigidity, second is for depth, third is for the pore pressure or 3-dimensional consolidation. Okay, so H by B was 2 by 6. Okay, so thickness is of the clay is 2 meter, diameter is of the tank is 6.33, and suppose a value is known, suppose 0.7. From the graph we get 0.62. After multiplying, so we get final settlement is 18.310 mm. Okay, so this is how we similar correction also can be applied for the first value which we discuss here. Also we can find out in the similar. Okay, so this is how a settlement expression is used for a different condition and to get the final consolidation settlement. Okay, so next part in this stress distribution chapter, now we'll move to the Newmarks influence chart. This is a great facility that any type of load, particularly the load has a shape, it is easy to find out the stress directly by using the chart, standard chart, which is made by this Newmarks. Okay, so this is used for any type of loading, particularly irregular loading, because we have seen that the vertical stress can be obtained for a standard geometry, circular, then rectangular, square, or maybe a magnet loading. Okay, but in a practice often the load is irregular. For example, a raft, not necessarily the raft is like a square or a rectangle, it has many offsets. Okay, so it may be in 2 parts connected at a different locations also. So therefore the conventional method will be difficult or very tedious by using those expression, dividing the geometry, dividing the given drawing into the regular geometry. Instead of that, this chart is very useful directly to find out the stress. Okay, so the it is based on the circular loading area. So basic of this chart is that circular load, and any loading acting on it is converted into the point loads. Okay, the basic concept is that on a circular load, okay, any point acting on that, multiplying that area, it is converted into a point load. Okay, so we know the vertical stress expression under a circular load at the center, sigma z is equal to q. It is in terms of the radius upon the depth at which the stress is required. So now we are finding this r by z. Let the small r is capital R just to facilitate it. So first dividing this q here and then taking on the right hand side, this is on the left hand side, then reversing the power, that is the 2 by 3, and taking 1 upon. So finally we get r by z, okay, as a 1 minus sigma z by q. It is actually 1 upon, so therefore power is minus 2 by 3. Okay, so stress sigma z, this sigma z can be obtained at any depth z by just loading, okay, the q intensity over the area with a radius r. Meaning is that to get the sigma z, okay, you have to load, you have to apply the load. Unless there is a q, there is no sigma z. Okay, at a given depth, you, if you know the stress and you know the depth, you can just find out the radius r. So you can find out actually the area of loading at which you get the required stress, or something like a dimensionless for sigma z by q, that intensity. Okay, so if I vary this intensity from 0 to 1, the interval of 0.1, any interval you can take, and substituting in this equation and find out this radius. So you will find that to get the stress level of 0.1, okay, you required to load the r by z as 0.27 multiplied by suppose z, you get the radius. That is the meaning of all these points, okay, which is explained here. So above table helps in fixing the size of area of loading under the given stress. Example, suppose sigma z by q is equal to 0.8 from the table, then corresponding r by z value was 1.387, then the r radius you get it as z into this. Okay, so if you multiply by the depth, you get the area. Okay, so you get the stress range 0.8. Similarly, suppose stress range is 0.7, okay, so you get the area of loading, that is 1.11 into z. Okay. Hence, for the same depth, different area of loading can be obtained. Okay, so meaning is that if I know the intensity and if I know the depth, suppose I can fix up the area of the. Suppose I want a intensity same even, okay, taking a different the depth, then also we can also have a different radius as it explained below. If a annular space between the two circles, okay, from the table, if I draw the first circle is suppose for r 0.6 and second circle is for r 0.7 of intensities 0.6 to 7 is loaded with the intensity q, then the difference of these intensities gives me 0.7 minus 0.6. So they are corresponding, the radius of loading are 0.6 and 7 are this 6 and 7. Okay, so the difference of these two radius, if the load is applied on a ring, okay, on this difference, then intensity still I get a 0.1 because it is the state difference. Similarly, if the annular space between the circles, suppose 0.7 and 0.8, any two successive, okay, 0.7 and 0.8, so you first load the entire circle of radius 1.77 into depth, and then second circle 1.387 into the depth, okay, and you subtract, okay, still the intensity is the 0.1. If an annular space between the two circle, okay, let us say 0.6 and 0.7 of intensity 0.6 and 0.7 is loaded, then it is because of the it is because of the stress sigma z upon q 0.7 and sigma z upon q 0.6. So the difference is still the same. Okay, so this ring of two successive radius, okay, any two value, the intensity remains same, though the radius goes on the changing. Okay, so therefore similarly the annular space between the circle, another example 0.7 to 0.8, is considered, then the difference is the same. This shows that the annular space between the two successive intensity space produces the same stress as that of the total stress. Okay, so the meaning is that even I take a 1 0 2 and the first circle, okay, and I try to find out the stress of 0 to 0.1, then also I get the same intensity. Okay, so that is the concept here, which is also explained. So meaning is that any difference of that two intensities, that is these two, this is the difference, delta sigma z by q is here in this case 0.1, it means that difference remains same, or delta sigma z is equal to cq. Here I shown. Okay, so either you take any two bigger size larger radius, okay, at depth z, you get the same difference. Similarly, the smaller size radius, okay, space is loaded, you get the same difference. So difference remain constant, so delta sigma z is equal to c q. Now if the angular space is divided into the n parts, okay, if I draw the rays by drawing the series of rays, if I draw the rays here and divide this ring into a number of parts, here also show the rays are drawn, okay, then the stress on the each part, on this one each part, okay, so this expression is for an entire ring, so divided by n part, both sides is divided by n, so delta sigma z by n, so it is ci into q. Okay, so this ci is equal to this c constant upon number of parts in a one ring. So if all 10 circles are drawn and a series of rays are extended, then we get total n parts. Now 10 circles means these 10 circles, okay, of course the 10th circle is the imaginary, so practically we plot the 9 circles. Okay, what is the radius? These are the radius multiplied by certain z required, okay, then we get all the 10 circles, practically 9 circles, and then extend these rays in all the 9 circles, okay, and measure the total parts. Okay, so for example, I'll show you the figure which you are going to draw. I hope you can see this. So all 9 circles are drawn, okay, and it is divided into the number of rays. These rays are extended, and I measure the total number of parts, okay, and that equals to, suppose, capital N. Number of part in a one ring are small n, number of part in the entire 9 circle after drawing the rays are the total n. So finally we get the expression here, multiplying n on both sides. This is for one part, such total n parts. So here we get total stress n ci into q. Now how do we plot this? Okay, draw all the 9 circles and generally 20 rays are drawn. Okay, the figure which I showed, 20 rays means the entire circle is divided into 20 parts. You can draw it to any part, you can make it 40 parts, 50 parts, or even 10 parts. Okay, the more the number of parts, the final result will be more accurate, okay, compared to the less number. Okay, so it is it is from the observation it is found that the 20 rays are sufficient, okay, based on our required precision. Okay, so therefore, and the C value which we are seeing, the 0.1 is also sufficient. A interval of 0.1, you can take 0.2 also, or 0.05 also. 0.1 is still a sufficient. Okay, so 20 rays drawn, so 20 parts, and C is 0. C is 0.1, therefore 0.1 upon 20, that is C upon N, is 0.005. Okay, so that Ci become an earlier expression 0.005 n into q. N is the number of parts covered by that plan, we'll discuss, and q is the intensity of that the loading plan. Okay, now we'll see the construction. This is a basic principle. Up till now we discuss. Now we'll see the construction and then the application of this chart. So construction of this chart, select a suitable scale. It represents the depth. Okay, because you can see r by z is equal to this value, therefore r is equal to z, so therefore r actually indicate the depth. Okay, which we have seen earlier also, that r is every time we write r is equal to in terms of z, so radius in a plan, okay, indicates actually the depth. So let us say select a suitable scale, it represents the depth. Let us say z meter is equal to AB cent, or AB centimeter is equal to Z meter. Okay, so when we plot, we require this AB centimeter, and that gives us the circle. Now for the construction, let us take this AB is equal to 4 centimeter with Z in actual depth at in situ depth is Z meter, then it represents the 4 centimeter. You can take any suitable value. Okay, let us say 4 centimeter. Therefore this AB is 4 centimeter, and convert those values earlier which were written for interval of 0.1 to 1 by multiplying it to the 4. So this 0.27 multiplied by 4, so I get a final radius in centimeters. Okay, r by z multiplied by z is multiplied here, okay, as AB centimeter is suppose 4, so I get this value. So I get the all 9 circle. So draw all the 9 circle, okay, preferably on the graph paper. Okay, so this is the figure. Again we'll see that here I shown this indicate AB as a scale. Okay, here I written the AB is 4 centimeter, which actually indicate the depth Z. Okay, so all these 9 circles are plotted. Okay, 1 to 9, and then the 20 rays, almost 18 degrees. Okay, so it is divided into the 20 parts. So this is the 1 part, 2 part, 3, 4, 5, 6, 7, like that. So this is called as a Newmarks chart of influence factor 0.005, because we are use intensity is C is 0.1, and number of rays or number of circle the parts we are taken as a is divided by 20. Okay, and here scale is a 4 centimeter. Now we'll see how to use this, the application part. If Z is the depth at which the sigma Z is desired of a given plan, suppose a raft is given, okay, in a plan, and it is asked to find out the stress at a depth Z, maybe at corner or a center, then scale of that plan, okay, scale of that load is AB centimeter is equal to Z meter. Therefore 1 centimeter is equal to Z upon AB. This is meter centimeter, therefore I convert in centimeter upon centimeter, like 1 into, I get something like a 200 or 100, something like this. Okay, for example Z is 4 meter, so it becomes 400. AB I selected 4 meter, so 400 upon 4, okay, 1 is 200. Suppose the depth of that the point where sigma Z is required 8 meter, then it is the 800, okay, divided by 4, so it is 1 is to 200. The scale of that the load is 1 is to 200. So this is how we plot. This after getting the scale, the drawing is plotted on a tracing paper, transparent paper, okay, with this scale, and then the point where we require the stress in a plan, okay, maybe corner, suppose a raft, rectangular raft at the center or corner, that point is overlapped with this Newmarks chart center. Okay, so you may get a suppose a square. Suppose the load is square, then it becomes like this. I require a stress at the center of square. Okay, then that center on the tracing paper and Newmarks chart both are overlap, and then you measure the number of parts covered by that plan to the scale obtained earlier. Okay, so using scale we draw the plan on the tracing paper, we mark the point where the stress is required and then overlap with this Newmarks chart, and we count the number of parts. That gives me the capital N value. Okay, and that capital when we multiply it to the 0.005 and its intensity of load, I get directly the stress. So this is how the application of the Newmarks chart. Now it will clear from the one numerical. We take it. Let us take a one numerical solid. So this is a raft given. Determine the sigma z at the center of the raft, 4 by 4 meter, and depth required exactly below the center is 4 meter. Okay, intensity is given as suppose 200 kilopascal. Now first find out the scale. Now the Newmarks chart is already drawn, and where the scale was AB is 4 centimeter. Now the depth at which this sigma z is required here is the 4 meter. Therefore AB centimeter equal to z meter, 1 centimeter equal to z upon AB. Okay, so z is 4 meter, and the scale of the Newmarks chart is 4. So 4 meter means 400 upon 4, 1 is to 100. Okay, it means 1 centimeter on the drawing represent 100 centimeter in situ conditions. So using 1 is to 100, draw this 4 by 4, okay, on a tracing paper, and then overlap this cube with the center of Newmarks chart and find out the total number of the parts covered by on the Newmarks chart. So imagine that this is a square. I mark here 4 point like this. Okay, and once we mark this, find out how many number of the clear parts means is covered the full. Suppose this should be actually drawn on the tracing paper. For example, I am drawing here on the directly on the Newmarks chart, so you get the idea here. Okay, so it means first circle, second circle, almost third circle, 1, 2, 3. Okay, they are the full part, and total are such the 20. So 1, 2, 3 into 20, 60. So directly I get the 60, and you can see after 1, 2, 3, this is the small part. I can take this and this as a 1. I can take this corner 1, this. Okay, so 60 is total number of full parts are 60, and number of that the fraction parts obtained, and they are converted into the equivalent full part are suppose 8, as I discussed earlier. So total are 68. So you multiplied by 68, so you get its substitute in the expression 0.05, 68 into 200, you get the 60. Okay, the same problem we have already solved by using the regular stress distribution concept. Okay, I can show you quickly. Yes, that's it. So here the same problem was solved using a direct closed form solution, where it was divided into 4 parts, and then finding m and n value, and substituting that the equation, we got the value as 67.2. where kb value was 0.0840 and that was 67.2, and from Newmarks chart it again depend how accurately you count the part is 68. So both are very close, therefore whatever the exercise we have done is correct, it is verified. So let us take the another example. This will be more simple. Okay, so determine the sigma z at the center of a circular footing 3.06 meter radius, resting at 2 meter below the foundation level. Determine the vertical stress, even the total stress also. But main our question is the sigma z or delta sigma z 4 meter below the footing. Also verify using our the closed form solution which we had earlier discussed. Okay, the contact pressure can be obtained from a load on the footing is given 2942. Okay, so therefore this is your circular load of a radius 3.06 and intensity is 150. So we require the stress at 4 feet. So we have the closed form solution. We will also verify from that. First find out the intensity, load upon area of this the plan is 100 kilopascal. Okay, now first by our the expression which we discuss. So radius is the radius is 3.04 divided by z 4 meter, you get 49. Now using a chart, now AB is equal to z meter, so this z upon AB is equal to 4 meter by 4 centimeter, 400 by 4, so 1 is to 100. Okay, now draw the plan of circular load 3.06 meter radius on a tracing paper and overlap the center of the circular area with the center of this chart. Okay, now these dimensions are taken so perfect that here the scale is 1:1, and when we plot the radius 3.06, okay, and here you get the 3.06 where exactly. You can also cross check here. This is the 3.0, so means the circle is first, second, third, fourth, fifth. The fifth circle having also the same radius 3.06. Okay, that's why I purposefully taken that. The fifth circle, first, second, third, fourth, fifth. Okay, so if you overlap the tracing paper, it also gives the same circle. That is the actual load, and center of that tracing paper, that is the area, and center of Newmarks chart. Okay, first, second, third, fourth, fifth. Count the number, total number of parts. 1, 2, 3, 4, 5. Okay, 5 into 20, 100, exactly 100. So therefore here I can substitute total 100 parts, so 0.005 100 into intensity is 100, so I get 50. From calculation I get 49.89. so they completely match. So you can see the method is very simple. Okay, useful for any shape, particularly the irregular shape. Okay, only the precision is that how you calculate full parts and fraction parts. Convert a fraction part into equivalent full parts, so you get the total number n. Okay, I suggest that try to solve this problem, because this is a very close situations. Many times, particularly now the metros are going on, and you can see here there is already one tunnel. Okay, and very close to tunnel is far much below depth. Okay, 4 meter, 6 meter. Okay, maybe even they have some guidelines also, sometimes 25 meter below. okay, the ground level. And there is a one proposed, suppose a high rise structure is there very close. You can see perpendicular distance at this point is 2 meter, at this point is 2 meter, and this is the proposed structure. The tunnel is already constructed, 10 meter, okay, this length, and total is 20 with this offset, okay. So this also represent a raft, and you apply a maximum intensity of suppose 500 kilopascal, okay. And the tunnel which is shown here, okay, the reach of the tunnel in the top portion is 8 meter below the bottom of raft, okay. The top of the tunnel, that is reach, is 8 meter below, and the side, if I draw this tunnel here like this, and the side distance is 2 meter away from the edge, okay. So tunnel start from this point to this point, okay. Determine the additional stress due to this raft or the tunnel, okay. So this tunnel, the linings, their roof is designed with a particular stress, and some linings are provided accordingly, okay. Here it is necessary to check whether that lining provided which are designed with a certain stress, whether that stress exceeds because of this structure, okay, that is, if it is not, then structure can be permitted also. If it is not, then it is asked to revise the design, or they may ask more offset also, okay. So again the procedure is same. First find out the scale. Here the depth mentioned is 8 meter, so Z by AB, our Z is 8, means 800 by 4, okay, that is 200. So 1 is 200 is the scale. Using that, draw the plan on a tracing paper, okay. Now what is the question? To find out the stress at point A, B, which is exactly center, and the C, okay. So on a tracing paper, 1 is to 100, draw this, mark this distance, draw the edge line, draw the one edge line, okay, and mark the point A, B, C. Now overlap the point A with the center of the Newmarks chart, okay, only A, and count the number of parts covered by this raft on the Newmarks chart. So you get the N value, okay, Q value is given, find out the stress. Second time you overlap the B point on the center of the Newmarks chart and find out the number of parts. Similarly at the C, and you can determine the stress at A, B, C, okay. So this is how you can find out the stress, okay, at the required point, and this is how we discuss the Newmarks chart.